Assalamualaikum warahmatullahi wabarakatuh. Hello everyone, I am Putri Rizky and I'm from Winsunan Gunung Jati Bandung. And today we're going to delve into a fascinating dynamics of a mechanical system involving mass, a spring and a pulley. As you can see in the diagram here, our system consists of a large pulley with mass M, a spring with stiffness K, and also two hanging masses M1 and M2, and also a string connecting M1 and M2 over the pulley. A crucial detail, and one we've clarified for this analysis, is the springs connection. We are interpreting the diagram such that the spring K is attached vertically between the fixed support of the pulley M and mass M1. The string then passes over the fixed pulley, connecting M1 and M2. And how this system moves. Let's consider how the system behaves, especially given that M1 is greater than M2, as you can see in this video. 1. Initial movement. When the system is released, the greater gravitational pull on M1 will cause it to move downwards. Consequently, M2 will move upwards. 2. Spring interactions. As M1 descends, the spring K will be extended, exerting an upward restoring force on M1, opposing its downward motion. 3. Pulley rotation. The movement of the masses and string will cause it pulley M rotate. The pulley's rotational inertia will play a role in the system overall dynamics. 4. Damped oscillation. As you can see in this video, the problem statement explicitly mentions the presence of a damper. This means that after the initial descent of M1, the damping force will dissipate energy from the system. This energy dissipation will cause the system to eventually stop its initial movement. Following this, M1 will undergo damped oscillations along the y-axis, eventually settling at a new equilibrium position. In essence, we're observing a classic case of damped oscillatory motion. Constraints are conditions that limit the independent movement of parts within a system for our setup. We have a few key constraints. 1. Inextensible string constraint, and 2. Non-slip pulley constraint. This directly links the linear motion of masses to the angular rotation of the pulley. If M1 moves down by y, the pulley rotates by an angle, let's say theta, such the y is equal to r theta, where the r is the pulley's radius. So let's move on. How about degrees of freedom this system? The number of degrees of freedom, or DOF, is the minimum number of independent coordinates required to fully describe the system's configuration at any given time. Okay, considering our established interpretation, the pulley M is fixed in its translational position, only rotates, and the string links the movement of M1 and M2, and both of them is moved by y, and the non-slip condition links the rotation of the pulley to the linear movement of the mass. Therefore, the entire system's motion can be described by a single dependent variable. So the system has 1 degree of freedom. To find the equation of motion, we will utilize the powerful Lagrangian mechanics approach. This involves calculating the total kinetic energy T and total potential energy V of the system, and then applying Lagrange's equation like this. 1. Kinetics energy T. We have T for M1, M2, and roll. For the pulley, since the pulley have the inertia, I is half of mr² and y dot is r theta dot. So theta dot is y dot divided by r. And we have to roll like this. And also the total kinetics energy is like this. And the potential energy, it causes gravity and the spring. The same as like this, the gravity is Vg1 and G2 for M1 and M2. For the spring, let YST be the static extension of the spring when the system is in static equilibrium. Before considering any dynamic displacement Y, total extension of the spring at any point in time will be YST plus Y. So, potential at spring is like this. And total potential energy V is like this. So the Lagrangian is like this. Using Lagrange's equation like this, and also this have non-conservative force because, as mentioned, there's a damper. For the first equation like this. And the second equation is like this. But we have to know the tension and the spring force of the system is like this. Notes. So for the second equation for M1 is sigma F like this. Let's substitute the equation for M1. We have like this. And we have minus ky for the second Lagrange equations. And for non-conservative force, Q and C is like this. Let's assume a linear viscous damper with damping coefficient C, and the damping force would oppose the motion. So like this. And we have Q and C is minus C y dot. Let's substitute the equation. We have all of them to Lagrange equations. And we have y double dot like this as the equation motion of the system. So the equation motion for the system by assuming a fixed pulley, the spring between a fixed point, and M1 and a damper is like this. Thanks for watching, and I apologize for my mistake in this video.